So, very good morning, students. Welcome to IIT NEET Foundation or Focus C program by Krishnaveni Talent Schools and the Mastermind Schools. So once again, I welcome all the class 7th students of Falaknama branch so far for today's session. As you all can see on the screen, and you are well aware, my subject is physics. We are in class 7th. Today we are going to start a new chapter, chapter number 6, work, energy and power, which is going to be the syllabus for the upcoming test number 6, right? Which is on 30th December. And today we are in the session number 1. So there are 3 terms you can find which plays very important role in the physics. That is work, energy and power. So all these 3 are interrelated terms. They are connected to one another. They are not independent. Work is there, energy will be there, power will be there. Means all 3 are interlinked, interrelated. So in this chapter, for coming 4 to 5 sessions, we are going to discuss about the each and every term and various examples and how they are applicable in our day-to-day life. Right? So where you can see the application of work, energy and power in our day-to-day life. Right? So we'll move to the next slide to know more about the first term. Today we are going to discuss about the work. So everybody know the common word. It is a commonly used word. So you can see on the synopsis point also what we are going to cover. Learning objectives. That is, first we'll discuss about work. Then there are types of works and many more about the work. Then energy. Then the relationship between work and energy, which is called work-energy theorem. Very important. Then again, continuation, law of conservation of energy. So you all know that energy can be neither be created nor destroyed. Only thing is it can change into another form. So that is called law of conservation of energy. And finally, about power. What is power? Where you can applicable? What are the units of power? How to measure the power? Everything we learn in the topic power, right? So before that, today we are going to start with the first word in the chapter, that is work. So what is work? When you say work is done, see, we feel that we are doing a lot of work by sitting at one place, right? Sitting at one place from morning 8:30 to 6 o'clock, I'll sit in my place and I am doing so much work. That is work from our side, but physics point of view, that is not work. There is a different definition for the work in physics. So that we have discussed here. So work is nothing but when you said work is done, when the body changes its position. Okay. So exact definition, if you see, work is said to be done when a body displaces. When body displaces means changing the position. Displaces along the direction of force. Along the direction of force. Suppose the force, either it may be either push or pull, anything. So when you went to any supermarket or hotel, restaurant or at home also, when you want to open the door, either we push or we pull, right? If the door is opened, we can say that some work is done. If door is not opened, there is no work is done. Even though you are putting effort, even though you are applying the force, if the body displaces, then only we can say that work is done. If not, no work is done. Got it? Yeah, that is the definition of work. Now we'll see as per our physics. So work is said to be done when force produces the motion. Force produces the motion. So mathematically, W is equal to force into displacement. Force into displacement. The mathematical formula, F into S. W is nothing but force. Yeah, sorry, work. F is force, S is displacement. So we now measure the force in Newton, right? Newton is the unit for force. Displacement in meter. So Newton into meter, or you can kind of, you can measure this in the joule or erg, unit for the work, right? So work is said to be done when a body displaces along the direction of force. The body displaces along the direction of force, which is mathematically given by the force may be either push or pull. Either you are pushing or pulling, no matter. For example, when you sit on a dining table, your entire family is sitting on dining table for dinner, right? So many dishes are there in and around the table. So whichever you want, suppose you want rice, you want curd, or you want dal, you want curry, what you will do? You will push that vessel towards you. So when you are pushing, what happened? It is moves towards you. Or if somebody asks, you do the, sorry, if somebody asks, you push. If you want, you can pull. So in both cases, what happening there? You are applying some force and the ball is displacing from there. So we can say that some work is done. When there is no displacement, physics point of it is no work is done. For example, you are sitting in classroom. Classroom is very small one. Your 40 students are there. Example I'm telling you. So you feel very congested in sitting in the classroom. So you all friends decided that we'll push the wall. We'll push the wall so that room will become very big. You all together you're applying the force on the wall. But we cannot move the wall. But you are applying the force. Force is there. But there is no displacement, is zero. So what happened? Something into zero is nothing but zero only. Right? So if the body changes the position, then only you can say the work is done. If not, there is zero work or no work. Right? So that is about the work here, the definition of the work. So many examples you can see here. So example, a man climbing, right? A man climbing the stairs of the house, stairs of the house is also doing work in moving himself against the force of gravity. When you are climbing the stairs, your earth is attracting towards earth, that is gravitational force. But still you are moving up by applying some force, right? That is muscular force, whatever force it may be. So then that is called as a work only, right? So next, the mathematical expression I told, work done is equal to force into displacement. Force into displacement. So the work done by a force on a body depends on two factors. So work done mainly depends on two factors. One is magnitude of force, that is F. Magnitude is how much force you are applying. More force you apply, more work may be done. Then distance through which the body moves. So distance. These two are the very, very important factor for work to be done. So one is force, other one is displacement. These are the two factors where the work done on a body depends. Okay. So they are given. So work done is W is equal to F into S. Force is dyne in CGS, Newton in MKS. So dyne centimeters or Newton meter. Already I told you. Dyne centimeter or Newton meter is also called erg. Right? That is W is equal to F into S. This is about the basic information of the work. So more is there. How many types of works are there? We'll discuss. Before that, let us go through this video. After seeing this video, after watching the video, I'll explain the further what are the different types of works we'll come across in our day-to-day life, right? Please watch this video. Then we'll move to the next part of the work. Just this is animated video explaining about the.
I have to do lots of work. I'm so tired. I don't have any more energy now.
Mom, why do you need energy?
Son, we do lots of work daily. Reading, writing, thinking, cycling, etc. So we need energy to do all these activities.
Mom, this washing machine also does work. Does this also need energy?
Yes, but there's a difference. Come, I will tell you about the work and the energy.
Objectives. At the end of this lesson, you'll be able to define work and energy, write different forms of energy, write the expression for
Our
kinetic
entire
and potential
topic
energy,
we are going to discuss in this chapter.
understand the laws of conservation of energy, define power,
See,
write the units of work, energy and power.
so these are the total topics what we are going to cover in this chapter: work, energy, and power. So once you see the video, then we'll move to the whatever is required now. Is all the topics. Already I shown the first page of our material where you can find all these topics. Okay. So this video will help you a lot in understanding the concept.
Work. Friends, we do lots of work like playing, studying, cycling, running, etc. All these works require a lot of energy. But the scientific definition of hard work may involve very little work. Let's see how. Look at this huge truck. We work hard to push it, but the truck does not move despite all the effort. We get tired. However, we have not done any work on the truck as there is no displacement of the truck. We can say that we did hard work, but in science, the work is not done on the truck. We use and define the term work differently in science. For example, if we climb up a cliff, then according to science, we have done lots of work. Scientific conception of work. For work to be done, these two conditions should be satisfied. First is, a force should act on an object. Second is, the object must be displaced. Let's take a look at a few situations. If we pull a table and the table moves through a distance, here we have exerted a force on the table and it is displaced. So both the conditions are satisfied here. Therefore, work is done. Similarly, while playing cricket, if we hit a ball with a bat, then work is done because force is exerted on the ball and that ball is displaced. Work done by a constant force. To understand the concept of work in science, let us consider a case. Case is, the force is acting in the direction of displacement. Let a constant force F act on an object. Let the object be displaced through a distance S in the direction of the force. Let W be the work done. We define work to be equal to the product of the force and displacement. Work done is equal to force into displacement, or W is equal to F into S. Thus, work done by force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Work has only magnitude and no direction. If F is equal to 1N and S is equal to 1M, then the work done by the force will be 1 Nm.
I told already.
The unit of work is Newton meter or joule. Thus, 1 Newton meter or 1 joule is the amount of work done on an object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. Example. Let's now find the work done when force applied and displacement is given. A student lifts his school bag from the ground and puts it on his shoulders. 1.5 meter above the ground. A force of 5 Newton is acting on an object. Calculate the work done by him on the school bag.
This you can find in the
We can see that here force applied is 5 Newton and displacement S
1.5.
is 1.5 meter. We know that work done is equal to force into displacement. Therefore, we get work done is equal to 7.5 Newton meter or 7.5 joule.
right.
Energy.
So before
We now know that to do any kind of work, we need energy. We must have energy to accomplish work. But the question is, where does this energy come from? The sun is the biggest natural source of energy to us. Many of our energy sources are derived from the sun. Energy sources are classified into 2 groups: non-renewable and renewable. Most of our energy comes from non-renewable energy sources: coal, petroleum, natural gas, propane, and uranium are non-renewable energy sources. They are used to make electricity, to heat our homes, to move our cars, and to manufacture all kinds of products. These energy sources are called non-renewable because their supplies are limited.
limited. We cannot use
Renewable energy sources include biomass, geothermal energy, hydropower, solar energy, and wind energy. They are called renewable energy sources because they are replenished in a short time. We use renewable energy sources mainly to make electricity. An object having a capability to do work is said to possess energy. The object which does the work loses energy, and the object on which the work is done gains energy. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy is, therefore, the same as that of work, that is, joule.
So both
1 joule
energy are
is the
same.
energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule is used. 1 kilojoule equals 1000 joules.
So this is about the energy part.
Forms of energy.
There are different forms of
There are many different forms of energies. These various forms include potential energy, kinetic energy, heat energy, chemical energy, electrical energy, and light energy. Let us first study about kinetic energy. We know that a moving object can do work, and an object moving faster can do more work than an identical object moving relatively slow. Kinetic energy is the energy possessed by an object due to its motion. The kinetic energy of an object increases with its speed. Turning wheel, moving car, boy running are the examples of kinetic energy. So we say that the kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity.
So this is one kind of energy which is due to motion. When body is in motion, we'll get the kinetic energy. One form of energy. Next, you can see the next type.
Equation of kinetic energy.
Mathematical equation.
Let us now express the kinetic energy of an object in the form of an equation. Consider an object of mass m moving with a uniform velocity u. Let it now be displaced through a distance s when a constant force F acts on it in the direction of its displacement. We know that the work done W is Fs. The work done on the object will cause a change in its velocity. Let its velocity change from u to v. Let A be the acceleration produced. The relation connecting the initial velocity u and final velocity v of an object moving with a uniform acceleration a and the displacement s is v square minus u square equal to 2as. This gives s is equal to v square minus u square whole upon 2a. We know that F is equal to ma. So by using values of F and S in the equation of work, we get W is equal to ma into v square minus u square whole upon 2a. Or we can write it as W is equal to 1 upon 2 into m into v square minus u
Here we can
square.
cancel out the A and A.
If the object is starting from its stationary position, this is
A cancel.
u is equal to 0, then the work done, W is equal to 1 upon 2
Of
into mv square.
Half into mu square.
It is clear that the work done is equal to the change in the kinetic energy of an object. Thus, the kinetic energy possessed by an object of mass m and moving with a uniform velocity v is 1 upon 2 mv square.
So this is the formula for the kinetic energy. So the energy possessed by a body due to virtue of its motion. Every moving body produces kinetic energy. Right?
Example. Let's now find the kinetic energy of an object of
mathematical
mass
example.
10 kg which is moving with a uniform velocity of 4 meter per second. Solution. Here mass of the object m is equal to 10 kilogram. Velocity of the object v is equal to 4 meter per second. From equation of kinetic energy we get
Half a
1
meter.
upon 2 into 10 kilogram into 4 meter per second into 4 meter per second,
Where is
which
this?
is equal to 80 joules. Hence, the kinetic energy of the object is 80 joules.
Right. The next form we'll see. Potential energy.
Potential energy.
The second form
To
of
understand potential energy, let's do an activity. Take a rubber band, hold it at one end and pull from the other. You will see that the band stretches. Now release the band at one of the ends. What do you see? The band will tend to regain its original length.
elasticity.
This means that the band had acquired energy in its stretched position. Do you know how did it acquire energy when stretched? Here the energy gets stored due to the work done on the object. The energy transferred to an object is stored as potential energy if it is not used to cause a change in the velocity or speed of the object. We transfer energy when we stretch a rubber band. The energy transferred to the band is its potential energy. The potential energy possessed by the object is the energy present in it by virtue of its position or configuration.
Right? Being in the same position, it can produce the energy. That is called potential energy. Right?
Potential energy of an object at a height.
So in
Gravitational potential energy is the energy stored in an object as the result of its vertical position or height. Let's find out the expression for the gravitational potential energy of an object at a height. Consider an object of mass m. Let it be raised through a height h from the ground. A force is required to do this. The minimum force required to raise the object is equal to the weight of the object. The object gains energy equal to the work done on it. Let the work done on the object against gravity be W. That is, work done, W, is equal to force into displacement, which is equal to mg into h, which is equal to
the
mgh.
mathematical formula for the potential energy.
Since work done on the object is equal to mgh, and energy equal to mgh units is gained by the object. This is the potential energy of the object. Also, the work done by gravity depends on the difference in vertical heights of the initial and final positions of the object, and not on the path along which the object is moved. Conversion of energy. Answer one question now. Can we convert energy from one form to another? Yes, one form of energy can be converted into another form. Let's take a small example. When we switch on a bulb, the electric energy is converted into light energy. Similarly, when we plug on the TV, the electric energy converts into heat energy, sound energy, and light energy.
Right. So we'll see later about the power and all. Next video will continue the same video in the next class, because what we required is we got now, that is about. Okay. Now we can see we'll back to our explanation part. So that video clearly explains us what is the work done and what is the examples of work done, which we already seen in the first slide. Then we have seen the units of work done, which is joule or erg or Newton meter or dyne centimeter. Okay. Now, work done against the gravity, the next part. See, there are three types of works are there. So there are, how many works are there? Three types. Number one is positive work. Right. Number two is negative work. And third one is zero work. Right. Positive work, negative work, zero work. I'll tell you. So for example, you have a block of wood on table or book in table. You can say book, this is on table. So you are pulling this one. You are pulling towards you. So you are pulling in which direction? The same direction book is also moving. If you push, it will go away. If you pull, it will come towards. So this is called positive work. The work done by a body along the direction of force. Suppose when you are pulling the table, when you are pushing the anything, what happened in this case? The force and displacement are in same direction. Right? In whichever direction you are applying the force, body moves in same direction. That is called positive work. Whereas negative work, you can see here. Suppose a body is on floor. You are lifting. So when you are lifting, the gravitational force acts in downward direction. So gravitational force pulls the body downwards, but you are moving against the gravitational force in the upward direction. That is called negative work. Means the work done and displacement are not in same direction. They are in the opposite direction or some other direction. It is called negative work. That is second case. In case, as you know the formula, W is equal to F into S. You are applying a force, but work done is zero. We have seen previous example. Or you are not done any work. Work done is zero, force is zero, displacement is zero. Any one of this is zero or both are zero, the work done is zero. That is called zero work. And there is one more is there. Suppose when you are applying the force like this in this direction, body moves in this direction. Displacement. Like a road roller. Road roller you might have seen. Driver will move the wheel and wheel will go in the other direction. He is applying the force in downward direction. Wheel move the horizontally, making some angle with each other. Right? Some angle theta. So in such case, the formula is W is equal to F into S cos theta. So this comes in trigonometry, you'll come across in the higher class in mathematics. So whenever the angle is become 90 degrees, when the force and displacement are perpendicular to each other, so cos 90 value is 0. So the total work done becomes 0. Example I will tell. In railway station or bus stop, a porter, coolie, will carry the luggage on head and moves to a platform. So his weight is acting in downward direction. He is moving horizontally with an angle of 90 degrees. That means, as per physics, he is not done any work. Work done is 0. He is doing work. That is generally he is doing work, but as per physics, because his force, the force is acting 90 degrees to the displacement. So the work done by the porter is 0. So don't say that you are not doing any work, I won't give money. As per physics, it is correct, but generally it is work done is there. And that is called negative work. So work done and displacement are in different direction. The best example is work done against the gravity. Right? That is comes under one positive work, negative work. Examples also given here. So many examples are given. Go through them. Okay. And third one is zero work. Zero work also there. When there is, already I told. And either force may be 0 or displacement may be 0 or both may be 0. then we can say that work is not done. That is called zero work. See, if S is 0, you are applying force on a body. Lot of force you are applied. You have seen in the video also. When you apply the force, body is not moving, but still the work done is 0 only. Even though you are applying, you are putting more and more effort. See, the example is given wonderful. When a person carrying the suitcase on his head or on hits the head in walking the horizontally, the work done against the gravity is 0. Flying aeroplane. So many examples are given for the zero work also. Right? So this is completely about the work. So what we have done? What is work? Definition. Then types of works. When you come for types, number 1, positive work. Number 2, negative work. And number 3, zero work. Okay. So work is nothing but W is equal to F into S. When a body displaces along the direction of force, then work is said to be done. Simple. Which is measured in either Newton meter or Dyne centimeter or joule or erg. So there are 3 types of works are there based on the direction of force and displacement. If the body displaces along the direction of force, either pull or push, the work is said to be positive. If the body displaces against the gravity force applied, is called negative work, like a body lifting from the ground. And the displacement is 0, even though force is applied, it is called zero work. Right? So this is a clear picture about the what is work, what we have seen till now. So when you come to the next classes, we'll discuss about the energy and the relation between energy and work, followed by the what is power also. Okay? Energy is already you have seen video. The same video again we'll watch for knowing more information about the energy. So what is kinetic energy? What is potential energy? What are the other forms of energies? And what is the law of conservation of energy? Then finally we come to the power part also. Okay. So today we are completely clear about the work and types of works. Right or not? So this is your home task, homework you can say. Define work, mention types of works. So take the homework, write in your notebooks neatly, definition of work and units of work, followed by types of works, positive, negative, and zero. And give the explanation and examples. So many examples are given in the material. You select some of them, or you can write your day-to-day example also. So everywhere you can, without work, you cannot do anything. By sitting at one place, you cannot do anything. At any cost, you have to move to get some work is to be done. For that, we need energy or we need power. So all these are the interrelated words, interconnected words. Right? So that's all for today. Have a wonderful day. Thank you, students. Thank you.